Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 17, 2026, just about 6 days ago. It introduces a high-performance action tokenizer that enables a small VLM2 model to achieve a remarkable 96% success rate on the Libero benchmark without any robotics pre-training. The paper is titled ActionCodec, What Makes for Good Action Tokenizers? And as we'll see later, the results for training efficiency are really impressive. So, Figure 1 breaks this down into two main components. The top panels outline 4 critical design pillars: higher overlap rates for stability, a compact codebook, strong vision language alignment, and independent token relations. Then, the bottom graph demonstrates the impact on training efficiency using the small VLM2 model. ActionCodec, shown as the top line with stars, achieves nearly 90% success in just 5,000 steps, whereas the nearest competitor, Fast, only reaches about 39% at that same milestone. Alright, Figure 2 details the specific architecture behind ActionCodec. The left panel illustrates a perceiver-like transformer block, which uses cross-attention to compress variable-length inputs into fixed-size learnable embeddings. Moving to the right, the full pipeline encodes raw actions, passes them through a vector quantizer to generate discrete tokens, and then reconstructs the action. Crucially, the stack of loss functions on the far right, including time contrastive and clip losses, forces the model to learn representations that are semantically aligned, rather than just minimizing reconstruction error. So, Figure 3 quantifies exactly how these design choices impact performance on the Libero goal benchmark. Looking at the third block, the data reveals a massive jump, increasing the overlap rate from 26% to 70%, more than doubles the success rate to 86%. Conversely, the top block shows that adding more tokens isn't always better. Performance drops sharply when the budget hits 64, likely due to overfitting. Ultimately, the optimized model in Block 5 achieves nearly 88% success. Well, Table 1 now puts those design choices to the test against the full Libero benchmark. The most telling comparison sits in the lower section, labeled Small VLM2 plus Tokenizers, which isolates the tokenizer's impact by keeping the backbone constant. Here, simple methods like binning or string tokenization struggle, scoring around 50%. Even the strong competitor Fast tops out at roughly 90%. In contrast, ActionCodec immediately jumps to over 95% average success. When enhanced with blockwise autoregression in the final row, it hits a state-of-the-art 97.4%, outperforming even many models that rely on heavy robotics pre-training. Turning to Table 3, we see a comparison of inference speed and efficiency, which are critical for real-time robotics. The middle rows reveal that naive baselines like string tokenization suffer from extreme latency, sometimes taking over 30 seconds for a single step. In contrast, the bottom row shows that ActionCodec achieves the highest throughput at 22 actions per second, with a latency of just 0.9 seconds. By combining this efficiency with a 72% overlap rate, the model proves it can handle high-frequency control without sacrificing its 95% success rate. So, Table 5 dissects the specific components driving that high performance through an ablation study. Rows 0 and 1 show that without soft prompts, the success rate stagnates near 92%. But enabling soft prompts in row 3 pushes the score to 95.5%, proving they are vital for knowledge transfer. Comparing rows 2 and 3 reveals that residual vector quantization, or R versus Q, only adds a marginal 0.3% gain, confirming that perfect reconstruction isn't necessary. Finally, the bottom rows show the method works equally well with intern versus L and QN backbones. Wrapping up, 2 takeaways stand out. First, ActionCodec shows that optimizing for training dynamics, rather than just reconstruction fidelity, is crucial for stability. Second, hitting state-of-the-art results without robotics pre-training proves that better tokenization can unlock general-purpose physical intelligence in existing models. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.